It is July 21st, 1959. The world's first atom-powered merchant ship is about to be launched. On the ways of New York Shipbuilding Corporation in Camden, New Jersey, the nuclear ship Savannah is ready for its christening. Mrs. Dwight D. Eisenhower, the First Lady of the land, arrives at the shipyard in honor of this historic occasion. In a few moments, the ship will slide down the ways and signal the beginning of a new era for the American merchant marine. Maintenance of a modern American merchant marine, the responsibility of the Federal Maritime Board and the Maritime Administration, is vital to our nation's trade, commerce, and defense. An atomic ship, modern indeed, is also another demonstration to the world of the intention of the United States to employ the power of the atom for the benefit of mankind. The NS Savannah is a new kind of ship. Powered by an atomic reactor, it will be able to travel for 3.5 years without refueling. It is the forerunner of vessels which will be able to transport more goods of the world in less time and at less cost. The Savannah will be a combination passenger and cargo vessel, accommodating 60 passengers and a cargo of 10,000 tons. But it is, above all, a test ship. It is a floating laboratory through whose operation we will gain valuable experience for the construction and operation of better atomic ships in the future, to maintain the flow of foreign commerce of the United States and the free world. The idea for the ship was first advanced by President Eisenhower in 1955, when he suggested such a vessel as a demonstration of this country's dedication to the peaceful uses of atomic energy. In July of 1956, Congress passed legislation which made this construction possible under the joint direction of the Maritime Administration of the Department of Commerce and the Atomic Energy Commission. Because the power plant of the Savannah was to be of advanced design, development of the atomic reactor was begun before anything else. The Babcock and Wilcox Company in Lynchburg, Virginia, was assigned the task of designing the nuclear propulsion system. The government had selected a reactor type which had proved its reliability and safety in previous nuclear energy projects. But the problem was to design a specific reactor for merchant ship use. The final design was a complex 48 feet high, capable of atomic power equivalent in operation to 20 million gallons of fuel oil. The reactor, together with its associated equipment, was to be enclosed in a container 35 feet in diameter and 50 feet long. Here will be produced the heat needed to make steam to drive the ship's turbines. Meanwhile, in the offices of the naval architect firm, George G. Sharp Incorporated, the ship was being designed. The most obvious change from the conventional design was the absence of a funnel, but other important problems were thoroughly investigated. It was desirable that there be easy access to the nuclear power plant for refueling purposes. In this early design, the superstructure blocked the way to the reactor. The decision was made to relocate the superstructure. Now, the reactor could be easily reached from the deck. By now, design and testing of the reactor components was underway in Ohio. In the nuclear power plant of the Savannah, high pressures were generated. Tubing must be developed which can withstand such pressures. When a component meets the rigid standards, it earns the OK tag. The fuel to be used in the Savannah's reactor is uranium dioxide. Powdered fuel is pressed into pellets. Pellets are fired at high temperatures. pellets are loaded into the fuel rods. The ends of the rods are welded. This prevents release of radioactive material. Tightness of the wells is carefully checked by X-ray. More than 5,000 fuel rods are inserted into an experimental test core of the reactor in Virginia. Now, a series of vital tests begins. Water serves as a neutron moderator and reflector in the fission process. Up come the control rods, and the chain reaction starts. Now, the scientist has a chance to test his theories in practice. Will the reactor design prove itself in operation? Is the right amount of fuel being used? Are the fuel rods properly spaced? Many questions must be answered. With the dropping of the control rods, nuclear fission is immediately stopped. While study of reactor design continued in Virginia, across the continent in California, special tests were conducted on the fuel to be used in the Savannah's reactor. A fuel bundle is carefully inserted into the test reactor core. At this stage, the fuel can still be handled manually with safety. After irradiation in the test reactor, it must be handled remotely with mechanical hands. The irradiated fuel is now ready for analysis. A fuel sample is measured in a radiation counter to obtain information needed to develop the most efficient fuel for the Savannah. May 22nd, 1958. Construction of the Savannah's hull is begun in the shipyard at Camden. At official ceremonies on Maritime Day, the keel is laid by Mrs. Richard M. Nixon. Before long, the ship begins to take shape. Like conventional ships, the Savannah will have a steam turbine to drive its propeller. The heat to make the steam will be provided by the reactor. The turbine and gears were being made in New Jersey by the de Laval Company. This bull gear, which will drive the propeller shaft, weighs 35 tons. But even huge parts such as these must be machined to close tolerances if the gear is to run smoothly and efficiently and to last the life of the ship. Its mating pinion gear is run against it to check for precise tooth contact. If there is the slightest flaw, irregular dye coloring will be transferred from one gear to the other. The turbine blades are milled 3 at a time by an hydraulically controlled machine. Then they are assembled to the rotor. This is the unit which will turn like a water wheel when steam is applied. The fully assembled propulsion unit, weighing more than 300 tons, was tested under full load conditions before it was ready for installation on the Savannah. In Barberton, Ohio, the boiler division of Babcock and Wilcox was busy forming the pressure vessel that will house the Savannah's nuclear power core. A huge press forces 8 inches of steel into a vessel cap. Because corrosion is an ever-present menace in any machine, the metal in the Savannah's reactor vessel is surfaced with stainless steel 1/4 of an inch thick. Meanwhile, at New York ship, the containment vessel is being fabricated. This huge shell will enclose the entire reactor system in order to contain any radioactivity that might be released during operation. One of the end sections is transported by barge to the ways where the hull is now being erected. 595 feet long, with a beam of 78 feet, 3,000 tons of steel have already gone into this construction. 4,000 more tons will be needed before it is finished. We are now approaching the reactor compartment where the power plant will be set. Redwood is to be part of the resilient collision mat which will line the sides of the reactor compartment. The mat will consist of alternate layers of redwood and steel and will protect the containment vessel against possible damage which might result through collision. The first layer of redwood is now in place, to be followed by a layer of steel. The center section of the containment vessel arrives at the ways and is prepared for placement in the ship. In the reactor compartment, a foundation of structural steel is prepared before the containment vessel is inserted. The 160-ton center section is now carried along toward its eventual position on the ship. The vessel is lowered very carefully. The two end sections, weighing 62 tons apiece, are welded to the center section. A cupola is mounted on top to house the reactor control rod drives. The next step is to insert the reactor system part by part into the containment shell. Using a small-scale model of the reactor complex, the designers were able to anticipate problems that would be encountered in loading the actual reactor components on the ship. Though it seems a simple operation here, the actual part weighs 20 tons. This is assembled to a steam drum to become one of the two nuclear boilers. Assembly time, 1 month. After the second boiler has been installed, the reactor vessel is lowered in place. The actual part weighs 110 tons and requires careful maneuvering. The 13.5-foot opening of the cupola allows at one point only an 8-inch clearance for insertion of the reactor vessel. Extreme care is taken with this operation. Within the containment vessel, workers secure the many parts in place. From the beginning, the Savannah was designed and constructed with the concept of safety as a paramount consideration. This cross-section view of the ship will permit us to observe the safety features incorporated in its construction. First, the reactor core is enclosed in a 6-inch thick pressure vessel designed to withstand 2,000 pounds per square inch. Around the pressure vessel is the primary shield consisting of a steel and lead tank filled with water. Surrounding the entire reactor system is the steel containment shell, which is designed to provide complete containment of any radioactive matter that might escape from the reactor in the unlikely event of accident. In addition, the ship's hull is specially strengthened to protect the containment vessel against damage from collision. The unusually heavy egg crate structure of steel in the bottom protects the ship's hull against being pierced through grounding. The collision mat of redwood and steel serves as further cushion against collision damage. The sway brackets support the containment vessel when the ship rolls. The upper portion of the containment vessel has been provided with additional shielding protection by an envelope of lead and polyethylene. A concrete wall 4 feet thick acts as an added shield against radiation. Finally, the base of the compartment has an insulating water shield. The Savannah, indeed, will be one of the safest ships afloat. The stern frame, which will support both the rudder and the propeller, is so thick that its parts could not be welded by hand. A process called thermit welding had to be used. Molten steel was produced in these crucibles and then allowed to flow into the joints, welding the parts together into one massive piece. After the steel had cooled, the 66-ton stern frame was installed on the ship. The single giant propeller, which will push the ship through the water at a speed of 20 knots, is carefully inspected. While construction continued at the shipyard, thought was being given to eventual voyages of the ship. States Marine Lines was selected as the operator of the Savannah. In a ceremony at the office of Maritime Administrator Clarence G. Morse, States Marine Vice President E.A. Terres signs the official documents. Meanwhile, in preparation for the Savannah's operation, the ship's engineers and deck officers were being taught how to operate the nuclear reactor and were becoming thoroughly familiar with its components. This training was conducted by the reactor designer in Lynchburg, Virginia. Foreign engineers, too, were encouraged to study the reactor. In President Eisenhower's words, the ship's design will not be secret. It will be possible for engineers not only of our own country, but of other nations, to view the nuclear power plant and see at firsthand this demonstration of the great promise of atomic energy for human betterment. By means of this simulator, which is a duplicate of the control console on the Savannah, the student was able to experience the same instrumentation responses he would get in actual operation of the Savannah. Training continued at the shipyard too, where crew members and maintenance personnel became familiar with the components of the reactor by means of this full-scale mock-up. Of course, these bolts, which seem easy to handle here, weigh over 400 pounds apiece in the actual reactor. And so the construction phase of the NS Savannah reached its climax. A final check was made by the inspectors, and the Savannah was prepared for a most momentous day of its life, its launching. Prominent guests are on hand to wish the Savannah well. They include Senator Clinton P. Anderson, chairman of the Joint Congressional Committee on Atomic Energy, John A. McCone, chairman of the Atomic Energy Commission, and Frederick H. Mueller, Secretary of Commerce. Many speeches of tribute are made. This is Maritime Administrator Clarence G. Morse. Another speaker is Representative Herbert C. Bonner, chairman of the House Merchant Marine and Fisheries Committee. The moment everyone has waited for arrives. Mrs. Eisenhower mounts the platform. July 21st, 1959, the world's first nuclear-powered merchant ship is launched. With the birth of the Savannah, a period of outfitting, dock trials, and then sea trials begins. By fall 1960, the NS Savannah will join the United States Merchant Marine, the first of a long line of atomic ships of the future, to help carry on the peaceful trade and commerce of our nation and promote liberty and freedom.